Hi everyone, my name is Deepak and I'm presenting the project proposal for BuzzTrace. The goal of this project is to understand the architectures of modern open source observability tools and integrate them with BuzzBlog, which is a microservices application that allows users to like, post, and share content. Most of our daily lives revolve around software, right? Whether we are buying a shoe from an e-commerce website or playing a video game or even undergoing a critical surgical procedure, the chances are that it involves an arsenal of software systems interacting with one another. And these software systems have undergone a series of metamorphoses over the past 2 decades. The figure in the slide depicts the software stack of a web-based application in the late 90s. As you can see, the entire stack ran on a beefy machine and consisted of serving dynamically generated interactive HTML content that gets rendered on a browser. Whereas tech stacks of the modern day look like this. As you can see, it's a much more distributed, diverse, service-oriented architecture with loosely coupled components, right? And moreover, the entire stack is polyglot with different stakeholders maintaining each service with different services which could change over time. And it's expected to run on an array of different hardware infrastructure ranging from cloud providers to developer machines to QA environments to air-gapped on-prem instances with strict regulatory compliance. Right? And a staggering metamorphosis of software systems was fueled by certain trends in the tech industry. So let's look at them as they're important to understand the motivation behind the project. So the evolution of these trends are explained in detail in the project proposal document, by the way. So in this slide, we'll just be naming them. So this is the so one first trend is that of the REST architecture, and the next one is migrating from monoliths to microservices. Parallelly, there is a trend to transition systems to the cloud, and then there was a trend pertaining to the automation of developer operations, and then there was always the triumph of open source software. So open source software has been around ever since Richard Stallman launched the GNU project. Then Linus Torvalds chose a lesser known path of building an entire operating system in public and offering it for free. Since then, one can see a clear trend in open source software winning against their proprietary counterparts. I would like to clarify here that it's not necessarily a dichotomy where open source software is pitched against tech giants. In reality, it is those very tech giants that fund these open source projects so that they can offer hosted services as a premium. The trend of open source software being adopted by tech giants to offer such services, are clear in these projects. For example, Kubernetes, right? Kubernetes was an open source software by Google, but Google GCP also has a premium service called Google Kubernetes Engine. Similarly, Docker although is free and open source, there is a Docker Enterprise version as well. And then Spark by Databricks, Airflow, which was initially open source by Airbnb, now branched out to Astronomer, and ClickHouse by Yandex. Right? Oftentimes, there is a battle between tech companies to get the core contributor of an open source project as their employee, so that the said company can gain more control over their cloud offering. And as software systems became complex, observability became an important aspect of software architecture right from its inception. In fact, there is no point in deploying an architecture that can scale from 10 containers to 100 containers based on user traffic if one has no way to measure the set traffic. An even disaster situation is when you have hundreds of microservices running, and 100 is not really an exaggeration because it's quite typical these days for even startups to have 100 microservices, right? And when you have these swarm of microservices running, and when you don't have any observability tools that can detect and alert based on the health of these microservices, it becomes notoriously hard to manually verify that the entire system is actually healthy and live. And this is where observability comes in. The popular book Distributed Systems Observability by Cindy Sridharan concludes that the three pillars of observability are logging, infrastructure monitoring, and tracing. So this project will focus on the later two. So what is monitoring? Monitoring is the process of collecting health and performance-based statistics from software infrastructure, typically in real-time fashion, without adding significant overhead on the system being monitored. So these stats are often stored in a time series data store and used for setting up important alerts, elastically scaling the system based on a combination of metrics, or even to power dashboards that provide a bird's eye view of the entire system's performance. Right? And in this project, I'll be extensively exploring and using an open source monitoring tool named Prometheus. Prometheus is one of the first monitoring software that follows a pull-based metric aggregation model with enabled service discovery, especially suited for dynamic cloud workloads. Hence, it kind of ticks all the trends that we described in the previous section. And it was, in fact, a fork of Borgmon, which is an internal monitoring tool used by Google and is currently maintained by SoundCloud. Next, let's look at tracing. What exactly is tracing? So, debugging software that runs as part of an HTTP request response cycle is hard. It requires recreating the right state and reading this exact API request that caused it to malfunction or degrade in performance. And the process of inspecting software, basically the process of inspecting software with an aim to identify latency bottlenecks or causes for degraded performance by dividing the entire life cycle of an event, such as an HTTP request, to smaller units called traces, is called tracing. And when the event being traced, passes through multiple nodes, then the process becomes much more complex, and this process is termed as distributed tracing. In this project, I'll be exploring and using an open source distributed tracing tool called Zipkin. It's a tool developed at Twitter that helps gather timing data needed to troubleshoot latency problems in microservices based architecture. Let's look at the proposed work. BuzzBlog is an open source microblogging application used for the performance study of microservices based systems. As with Twitter, users can write content, like them, and follow other users. The functionalities of the application are implemented by backend services with small scope conforming to the microservices model. The application comprises of different microservices responsible for accounts, posts, likes, followers, trends, etc. This project aims to integrate BuzzBlog with state-of-the-art open-source observability tools like Prometheus and Zipkin. These tools expose real-time stats pertaining to the application's health, resource utilization, and trace information across different checkpoints within the application. These metrics would then be streamed to a time series database and used to power multiple dashboards to provide a holistic view of the system. The fetched time series data would be used to plot visualization using the dashboarding tool, and this case, we'll be using a tool called Grafana. These stats would be contrasted with those obtained from Milliscope. Additionally, this project aims to instrument BuzzBlog code base with custom monitoring and tracing logic that would provide rich telemetry information of API requests as they transition from one microservice to another. This trace information is then aggregated by Zipkin to help us exactly pinpoint any degradation in performance of any of the microservices traversed by the request. Hence, this project in a way aims to reuse open source tools to gain insights into the health and performance metrics of an existing application. This would provide BuzzBlog an arsenal of additional metrics collected in real time and dense trace information pertaining to necessary checkpoints with their latencies. Prometheus uses open source exporters for different components to scrape metrics. These exporters periodically pull the relevant metrics over TCP ports from their respective targets. Since BuzzBlog consists of mainly web servers, a Redis cache, and many Postgres databases, I intend to leverage the freely available and open source exporters for Prometheus. They are the Prometheus Redis exporter that scrapes relevant metrics from Redis and stores them in TSDB. So it can be used to obtain metrics like commands per second, command latency per second, hit ratio, for instance, total memory usage of the Redis cluster, and even number of key evictions per second. And we can even use the Prometheus Postgres exporter, which can be configured to export metrics from each of the Postgres databases used by different microservices of the application. It can expose critical metrics like the current QPS, database deadlocks and conflicts, cache hit ratio, number of active DB connections, and buffer-related metrics. The Prometheus Flask exporter exports important web server metrics from ASGI/WSGI web servers. In this case, we are using Flask because BuzzBlog is written on Flask. It can collect server metrics like requests per second, errors per second, average response time, P50 latency, P90 latency, RAM and CPU usages. Right? And we can also use Prometheus client libraries available in almost all popular languages to instrument Prometheus metrics directly into our application code base. We can create custom metrics of our interest. For example, if you want to know the number of times a certain exception in our code was raised for users of a given region in the last few hours, we can actually achieve that by using custom instrumentation. Using Zipkin, we'll add custom traces. to the web servers making up the microservices application. Zipkin offers client libraries too, like Prometheus, in different programming languages that allow us to add checkpoints in our code base that asynchronously add the relevant span when a request passes through the checkpoint. And these spans are aggregated at the server level. Right? This slide depicts the system architecture of the project. The figure on the bottom right corner is the architecture of BuzzBlog application with the relevant links to different microservices. The application is instrumented with the necessary logic and deployed as containers. Either we can deploy it to a Kubernetes cluster or even to a single node using Docker Compose. And the components on the top right corner are Zipkin and Prometheus nodes that scrape the observability metrics and powers the Grafana dashboard on the left. The overall project is mainly divided into 4 stages with bi-weekly milestones. The table in the slides summarizes the plan to complete the project in phases alongside the meta skills being targeted for each milestone. To keep the presentation brief, I'll skip the explanation as to why a certain milestone requires a given meta skill, as that explanation is present in the project proposal document. As part of phase one, I'll be setting up the BuzzBlog application locally using containers and will acquaint myself with the code base and also the different microservices that I intend to monitor. I'll also dig deeper into the system architecture of Prometheus and provision its components on Azure. Although this step looks simple, it involves understanding the architecture of monitoring tools that evolved from simple heartbeats to pull-based models with service discovery targeted for dynamic cloud workloads. Hence, this phase would entail meta skills such as trend recognition and learning experience of a perishable but repeatable process. As part of phase two, I'll be integrating Prometheus exporters with BuzzBlog and adding custom instrumentation to the application code base using one of the client libraries offered by Prometheus. As custom instrumentation is a highly debated and opinionated topic, it has evolved to use advanced design patterns to ensure dependency injection and loose coupling between the observability tool itself and the application code base. Hence, this phase two involves trend recognition and learning experience of a repeatable process. Similarly, as part of phase three, I'll be setting up a dashboarding tool named Grafana and would proceed to understanding the system architecture of Zipkin. As part of phase four, I'll then instrument the code base with Zipkin traces to capture span information of different API requests and display them on a dashboard. These phases too involve trend recognition and learning experience of the repeatable process. Finally, I'll contrast the obtained metrics and trace stats with those obtained from our advisor to ensure correctness. Also, I'll be contrasting the extensibility and maintainability of using open source tools. This phase involves a distinction between fact and fiction, where we'll gain first-hand experience to justify the trade-offs involved in using open source tools against proprietary or in-house developed software. Thank you.